Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
Inside a modern high-performance engine, conditions are apocalyptic. Metal components move at tens of thousands of RPM. Without one critical, microscopic layer of protection, this feat of engineering would fuse into a solid block of scrap metal in seconds. Welcome to our comprehensive masterclass. We are looking at the molecular battlefield inside your engine to settle the debate: synthetic versus mineral. To understand why we need oil, we first have to understand the enemy, friction, and wear. Even polished metal has asperities. The goal of lubrication is to separate these surfaces with a fluid film. This brings us to the most important property, viscosity. In fluid dynamics, this is governed by Newton's law of viscosity. T is shear stress, M is dynamic viscosity, and do/die is the velocity gradient. In a high-performance engine, that velocity gradient is massive. The oil must maintain viscosity to support the load while flowing to remove heat. If viscosity is too low, the film collapses. If it's too high, the engine wastes horsepower pushing thick oil around, causing fluid friction. So how do we get the perfect fluid? Let's look at the baseline. Mineral oil. It starts its life deep underground as crude oil. At the refinery, crude undergoes fractional distillation. Engineers separate it by weight. Lubes are right in the middle. Because it's refined from a natural substance, its molecular structure is chaotic. You have mixed chains and waxes. It also contains naturally occurring impurities like sulfur and nitrogen that distillation simply cannot completely remove. When mineral oil gets extremely hot, like near the exhaust valves, lighter molecules evaporate, leaving behind a thicker, sludgy fluid. Meanwhile, the unstable molecules react with oxygen and heat to form carbon deposits and varnish. This is thermal oxidation. On the opposite end, in freezing temperatures, the wax molecules inherent in mineral oil begin to crystallize. The oil thickens up. This means during a cold start, when 75% of engine wear occurs, the oil struggles to pump to the top of the engine. To understand the full spectrum, we need to talk about the American Petroleum Institute's base oil groups, I through V. Group I and II are conventional mineral oils. Group I is solvent refined, while Group II is further hydroprocessed for better purity. Group III oils are severely hydrocracked under high pressure and heat. These are often marketed as synthetics in many markets. But the top tiers are Group IV and V, enter synthetic oil. Think of it as a bucket of perfectly identical glass marbles. Synthetic base oils are not simply refined, they are chemically synthesized. Engineers take pure molecules like ethylene gas. They chemically bond them together to build complex tailor-made lubricant molecules called polyalpha olefins, or PAOs. Then we have Group V esters. These are highly polar, meaning they chemically cling to metal surfaces even when the engine is off. Because synthetics are built molecule by molecule, they have no impurities, no waxes to crystallize, no volatile molecules to boil off. This uniformity gives synthetics a massive advantage in the viscosity index, staying stable from 0 degrees C to 120 degrees C. Synthetics resist thinning at high temps, maintaining an unbreakable hydrodynamic film between your crankshaft and bearings. Inside an engine, oil is squeezed through tight bearing clearances and smashed between gear teeth. This causes mechanical shearing. PAOs have inherently tough molecular bonds. They resist shearing, staying in grade long after mineral oil would have broken down. Now let's look at turbochargers. The turbine side is driven by exhaust gases that can reach 1000 degrees C. Heat is the enemy. When you shut off a hot engine, the oil flow stops. Mineral oil bakes into a hard carbon shell called coking. Synthetic oil's vastly superior thermal oxidation stability means it can survive this heat soak without coking, saving your turbo. Modern engines are built to incredibly tight tolerances. To flow through these microns, manufacturers specify very thin oils. It is physically impossible to make a stable 0W20 out of conventional mineral oil. You must use synthetics to achieve that cold flow. Under sustained extreme loads, synthetics transfer heat more efficiently because of their uniform molecular structure. How is oil performance measured? Through rigorous testing standards set by the SAE, API, and organizations like ASEA. Oils undergo sequence tests where engines run for hundreds of hours to measure deposit formation, sludge, and wear protection. ASTM standards define precisely how to measure flash point, pour point, and high temperature, high shear viscosity. But base oil is only part of the story. Up to 20% of your oil is an additive package: detergents, dispersants, and anti-wear agents. The most critical is ZDDP. It forms a sacrificial microscopic layer on metal parts during boundary lubrication. Friction modifiers use long-chain molecules to reduce internal drag, improving fuel economy and reducing surface temperature. Detergents neutralize acids, while dispersants keep soot suspended so they don't form deposits. Synthetics hold these better. Viscosity index improvers are polymers that expand when hot to counteract thinning. Synthetics require fewer Z-bonds than mineral oil. We also monitor the total base number, or TBN, which represents the oil's ability to neutralize combustion acids over time. In modern downsized turbo engines, we have a new challenge: low-speed pre-ignition. This can destroy pistons instantly. LSPI occurs when oil droplets ignite before the spark plug fires. Specialized synthetic additive packages are required to prevent this. Look for the API SP service category on your oil bottle. This standard specifically addresses LSPI protection and timing chain wear. Lubrication science is about managing the transition between hydrodynamic and boundary states. Synthetics excel in both. This is visualized by the Strybeck curve, which shows how friction varies with viscosity, speed, and load. Synthetics flatten this curve. Over time, oil degrades through oxidation and nitration. We track the total acid number, or TAN, to determine the oil's end of life. Used oil analysis is the best way to see how your engine is wearing. It measures ppm of iron, aluminum, and copper. High iron can indicate cylinder wall wear, while copper or lead might signal bearing issues. Synthetic oils consistently show lower wear metals. Don't forget the filter. Synthetic oils work best with high-efficiency synthetic filter media to capture microscopic particles. However, for older, low-compression engines or vintage cars with outdated seals, high-quality mineral oil is still effective. These fluids must be dielectric and provide extreme thermal conductivity. Synthetic chemistry remains at the forefront here. We are also seeing the rise of sustainable base stocks, where synthetics are derived from plant-based materials rather than crude. So, the final verdict. Is synthetic oil always the right choice? For high-performance machinery, it is a requirement. However, for older, low-compression engines or vintage cars with outdated seals, high-quality mineral oil is still effective. Remember, oil is the cheapest insurance policy you can buy. Always match the fluid to the application. We hope this 10-minute masterclass has given you the knowledge to make the right choice for your high-performance machine. If you found this breakdown helpful, like and subscribe for more engineering deep dives. Until next time, keep it running smooth. As a bonus, let's look at viscosity grades. The W stands for winter, indicating how the oil flows in cold conditions. High temperature high, shear viscosity measures the oil's ability to protect bearings under extreme racing conditions. Synthetic oils allow for extended drain intervals, but remember that the additive package still depletes over time. The NOAC test measures volatility. Synthetics have significantly lower evaporation loss than conventional mineral oils. Synthetics provide superior oxidation resistance, preventing the formation of varnish that can clog narrow oil passages. Their exceptional pour point means they flow instantly at sub-zero temperatures, where mineral oil would be solid wax. Anti-foaming agents ensure that air bubbles don't form in the oil, which could cause pump cavitation and loss of pressure. High solvency prevents the buildup of sludge, keeping internal oil passages clean for the life of the engine. Modern synthetics are carefully balanced for seal compatibility, ensuring they don't cause shrinkage or hardening of gaskets. It is a myth that you can't switch between oil types. Modern formulations are fully miscible and compatible with each other. Every machine is a symphony of moving parts. Oil is the conductor that ensures every component plays its part perfectly. We hope this 10-minute masterclass has given you the knowledge to make the right choice for your high-performance machine. Join us for the next deep dive into automotive engineering. Until then, keep your machines healthy, your clearances tight, and your lubrication running smooth.